I'm Oleg Sергienko, Doctor of Science. I'm working here in Skoltech as a research engineer of Artificial Intelligence Center, and also I'm head of Applied Physics Department in the University of Baja California, Mexican University. The topic is challenges in robotic navigation. And from this introduction video, I will show you some examples of challenges we did observe from time to time in several repetition of real practical experiments in our laboratory. We're living in the northwest of Mexico, and the typical landscape is like you can see on this video. So the robot in this condition don't move on the smooth flow. It moves every moment, suffering the changes of 6 coordinates, x, y, z, and also roll, pitch, yaw angles of self-positioning. And it is desirable for us know the moment of time when we exactly reading the information. You can see that the movement of robot, each iteration is not the same. It changed spatial orientation, and it's important to observe it. When the robot moving between any kind of obstacles, rocks mostly in this case, it don't need too much information provided by cameras. We don't need to answer the question, this rock is beautiful or ugly, wide or narrow, high, tall or low, brown or gray. Color in this case doesn't matter. We can conclude that for faster and more efficient decision, we must to filter unnecessary redundant information in order to take better decision in the navigation task. How we can reduce the quantity of information? Maybe you remember, I've mentioned before that camera, not very modern, not very smart. 20 megapixels, for example, give you 20 million of readings each second. This information, obviously, is not necessary to take a right decision on reply on the question, which side you must move. We will simplify step by step our task. We have robot. We have an obstacle located on the surface. In this example, you can see, by the way, that the navigation of drones, unmanned aerial vehicles, is much more simple because you don't have additional restriction by surface of moving. So surface is a member of this team. Then you need to define the scene, the real place where will happen the navigation act. And we decided on height, height, width, so on. Then you need to have any kind of scanning tool. In this case, I propose, for example, laser ray. Laser, you know what is it? Light amplification by stimulated emitter radiation. Straight, colored typically ray, which can reflect only on the physical obstacles, not from images, not from phantoms, so on. It's very important for further considerations. This is the simplest configuration of our system because, to be honest, it's not necessary even the scanning tool, because the second part of our system, laser detector, is original device patented 2 times in our university in 2017 and 2022. And this device can get information about presence or absence of light in the field when exists the light of necessary condition. So in darkness, if you want to detect the presence and coordinates of automobiles, for example, you can use the own lights of the car. But in the general configuration, active system have laser ray reflected on the surface of obstacle and then get the reflection in photoreceiver part. You can see that in every step, horizontal and on the lateral view, you can see vertical steps provided by step motors. And every step of these systems, you can form the triangle. Baseline, straight line, and reflected line. In this triangle, by use of simple trigonometrics formula, you can calculate coordinates of the points of reflection on the surface of obstacle. It's very useful. Why? Because you can see 4 points instead of all surface filmed by camera. It's significant reduction of information. You can tell me, maybe it's not enough. It depends only on you. The size of this step is adjustable. You can do it according to your application task, according to the striking distance you want, so on. How works this scanning? You can see here, field of view, dark rectangle, and a kind of obstacle. And you start to scan as a very old TV sets, line by line, row by row. When the reflection not exists, there is no any physical obstacle. The way is clean, you can go. And when you get the reflection, automatically you know X, Y, Z coordinates of each point, and you can see like 15 points are substituting the real surface. We are speaking about physical filter of redundant information, yes? It is more convenient to process by computer, and it requires significantly less computational cost. Yes? Here you can see the configuration of the scanner. It's static repetition of the same, but why this picture is important? I can show you here one very interesting thing, because when we are coming from the digital world to the real world, simple issues can help you to take a faster and more robust decision. For example, look, on the vertical surfaces, the density of points is more dense, yes? On the horizontal surfaces, the density of points is not the same. And you can detect it with detector. And then the decision unit can take decision. What kind of obstacle do you have? Hollow or salient object? Yes? Just simply evaluate and like a human being. It's big distance between dots or small distance. You can classify preliminary the type of obstacle. Here you can see some video explaining how works this system in real time and real life. And you can estimate without my commentaries how fast or how slow is it. Look, you can see here the obstacle on the optical table with very well-known coordinates on this point. And my ex-PhD student We'll try to find it with the laser ray and show you how fast appear every coordinate. The advantage of such system over the cameras is very obvious also, because in each point you know coordinates with preliminary setted meteorological quality. When you're working with camera can do the same, because the estimation of coordinate in cameras has a probabilistic character. This is important also. And now he will change the position on the table and trying to find it. In the manual mode, it's quick enough. But in automatic mode, it's much 1,000 times faster. Anyway, I must mention this velocity of this method is not the same like cameras. Because camera give you all information at the same time. And then you must spend a lot of time for processing. Here, we're obtaining information step by step in such quantity of dots which we need, which we want. Obviously, the first prototype shows several disadvantages. And this prototype was the first patented prototype. We did take to account all the mechanical imperfections of the movement, parasitic moment of inertia, so on. And we produce this aluminum prototype of 1 meter long between receiver and emitter. Who can tell me why exactly 1 meter? It's easy, because 1 meter is 1 in trigonometric calculation. You need to multiply 1 or divide by 1. You save the time. Yes? It works like show this video. Unfortunately, we can't hear the voice of my ex-PhD student. It was interesting because he was native German, Lars Lindner, and his accent is very different from mine. But you can see now only picture and comments. This is interesting note. This one. After the experimentation of the first prototype, we get understanding of simple issue, that the system is good, is precise, but lacks disadvantages. For example, stepper motor is quite precise, but on the long distances, it provides a kind of dead zones between the points highlighted by laser. So we decide to create any kind of mechanical transmission controlled by computer for ability to what? To change the size of step.
Значит, я посмотрел.
It wasn't my voice, neither Lars. So now for this moment, I think you understand more or less quite good how works this system. And I can mention some additional words. I've been the chair of the machine vision and navigation section in several biggest conferences of IEEE since 2014. Every year we are organizing the section on ISIE, International Symposium on Industrial Electronics, and ICON, the final big annual conference of IEEE. Normally it happened at the end of every year. October, late October, early November in different countries and different cities. The past one was in Chicago. The previous one was in Singapore, I guess, and so on. I do not remember all of them because I have a mix of conferences in my head. But I have one very interesting observation from all these conferences, and it gave me an invaluable experience. Many years I was struggling against, to say, camera lovers. They are trying to prove me that camera is much better than scanner. The quantity of such people is huge, but the quantity of people who likes rangefinders, adjustable rangefinders, laser scanners is not also. And this struggle, for a moment, I think, have no any meaning. Why? Because of issues of modern life. You know that United States have DARPA, Defense Agency. This institution have a multimillionary budget, and they provide robotic competition every year in California. They have a huge simulator of the city, and they pay significant prices from $2 million up to $6 million, I guess, for the winner of this competition. And I do not observe the last because they have no any fruitful, any interesting new solution, because they are going the same way last 10 years maybe. What they are doing? When I was observed the results of DARPA competition last time, win the team of Carnegie Mellon University. And always the winner is a big American university. Why? Because first, they use as robot a full-scale automobile. The last one was Volkswagen Touareg. They put there 64 different systems which measure own position and the vision of surrounding medium around. They are using lasers, about 1 million cost, and they use 16 lasers directed like an air fan in all directions, projecting the laser line. You can understand that the price of such device, it's several orders of magnitude, several times, obviously, maybe orders of magnitude higher than the price. How we can provide in real life such device for usual people use? It's impossible. But this trend exists to put all known systems because the budget not limited, and then use a very primitive mathematics. Which one? From 60 systems, 50 are concentrated in this value and 10 have a bigger error. So we just vote in 50 against 10. You know this is a winner. It's not bad strategy, but it's not smart strategy. Yes? So for a moment, I'm a little bit in the team of my enemies. I decide the good solution, according to the modern trends, it's combine different systems, but obviously not 64. even not 30. I suppose this decision is not bad. You can see here stereo camera, not very expensive, by the way. And you can see here the third version of our prototype of scanner, which we gonna to patent in the next year. Why? Because this is small scanner and it's 100% printed on 3D printer technology. It's plastic, it's cheap. Even the 45 degrees cut mirrors, we also printing and just put in there a plain mirror with the glue. So this laser is cheap. It's quite precise. You remember the disadvantage of this system is a long time of operation. But you have now 2 cameras here, and camera give you the preliminary image. This camera are cheap camera. By the way, preferably black and white. It's difficult to find on the market now black and white cameras, but it's preferable. Why? Because you don't need a color information. You need only positions of the objects on the pixels in the certain sectors of region of interest. And then you can give a command by computer to the laser positioner to scan region of the elevated interest. What it means, I will tell you later. Yes, later. Because I want to show you some further applications of this small printed laser scanner on the small printed robot. Almost everything here in this picture is printed. We are buying only precise electric motors as propulsor for wheels. What for? For this kind of practical application. To be honest, we have a lot of different application in this case. But this one is, to say, more fun, or I don't know. This robot for exploring of the internal surfaces of pipelines for gas, for water, for any kind of paper. And the use of such kind of technical vision system is absolutely unique. Cameras will not work here. Why? Can you tell me? Because it's complete darkness. It's kilometer of pipeline, no light there. Yeah. So this robot is going straight line and scanning lateral surface. Sorry. On the left, for example. And you know, in robotics, every device have resource. And when it's expanded in half, you must return for not to stay in pipeline for always. Yeah. On the return way, you are scanning the next semi-surface. You got it? I will back a little bit. So on this picture, one important thing which I forget, unfortunately. If the robot goes in this trajectory, to avoid the collision, you can go on the right or on the left from the obstacle, yes? Which trajectory is preferable? Can you tell me? Obviously not, because it's an arbitrary solution. But here in Russian Federation, I can finally tell the truth. If this is a civil machine, it's okay. no problem. But if this is a military machine, it is very important to avoid here a simple solution in algorithm. Because if you will go always on the left when it's the same, so your enemy will understand it quickly and will put obstacles. Especially for this machine, for what? For to make the turn on the left and put the left board on the straight line to weapon of enemy. Yes? It is better to take solution on the left or on the right using different kind of reasoning. I will tell further. Now we can go. Okay. Before to go to this stage of trajectory planning, by the way, in the American literature, this part is not called trajectory planning. They call it dead reckoning. Before to go to this part, we need to remind one interesting thing. Do you remember? Robots scan the surfaces of objects quickly, but spend some time. Meanwhile, it takes the image, the robot changes its own position, as well as inclination, roll, pitch, yaw. Yeah? It is extremely important for decision node of such navigation system to know on what moment of time exactly you got this reading. Yes? Are you agree? So, appear the next challenge in robotic navigation, the precise measurement of time. And where you can get the time on the robot board? From the onboard clock, isn't it? Usually, all devices in modern robotics are tending to be cheap. Yes? Because expensive things nobody will buy. So, the clock on board of the robot never is extremely expensive. Sometimes you have adjustment in connection with satellite reference clock, but it's time-consuming and expensive procedure. We need any more practical solution in this case. Which one? We need to measure time. You can see here on this diagram, time of the process. And how usually we are measuring the time? How many standards are inside the window of time? Indispensably, you are losing this gap and this gap. This is a principal source of error in the measurement of time. Who can help us? Mathematics. Simple mathematics started with the axiom of Archimedes, axiom Archimedes, 2000 years ago. And later inventions of Ostrogradsky, it's century 19. I will show you. Sorry. If you have this diagram, it's typical diagram for the process of frequency measurement in regular electric pulses. Train of pulses, unknown, you can see an upper part. And you can see the reference pulses. If you have a repetitive processes, like a cycle of scanning by laser, you can apply very simple thing. Which one? You can repeat and repeat and repeat again the same and try to find where the coincidence between initial point and final point will be more perfect with total overlapping. Yes? And you can see, if you will connect a simple AND gate, the cheapest, simplest electronic device here, you can find the coincidences. 1 and 1, you have a pulse. And these coincidences are appearing continuously. But they form like a package of pulses. You can see here the screenshot of real package of coincidences. Sorry. Where is the best solution, the best approximation? Here, where is no the rest, right? In the theory, this is a center of package. It looks like easy, but in real life not. Why? Because this ideal case, sorry. This is an ideal case, and pulses have no famous jitter. You know what is jitter?
Mm-hmm.
In the literature, it's like a slang word, but in the literature it's called arbitrary phase displacement of signal. So these pulses like moving a little bit. Because of this phenomena, the center can be displaced. This perfect coincidence will be like a partial one. It have no solution by the hardware, but it have an elegant and nice solution in mathematics. Look. In 1816, the famous British mathematician John Farey published the article about excellent properties of continued fractions, something like that. And he introduced this term, mediant. What is the mediant? Is a fraction obtained in the next way. You have one fraction, the second fraction, and you simply sum the denominator and numerator of both fractions. This fraction called as mediant. And look here, the magic of mathematics. The first coincidence here, we put the number 0. The second coincidence is after 3 periods of unknown and 5 periods unknown one. It's approximation. Really? It's good approximation. How good is it? It's defined by the difference of phase position of these pulses. But this is approximation. The next one appears 7 periods of unknown, 12 periods unknown. Also partial coincidence here. But look, the perfect coincidence, where is it? Here. Are you agree with me? And look, numerator of this fraction, 10. It's 3 plus 7. Yes? Look here, 5 plus 12, 17. This result we did publish in 2012, I suppose, in the Journal of Elsevier Measurement. And we call it the measurement of frequency by the principle of rational approximation by medians. With several experiments, but more simulations, we did prove that really where appear the fraction for formula of calculation of frequency, here you can see this, this formula. Known frequency, unknown frequency, and count of the periods until the perfect coincidence. So here, theoretically, you get the result with error equal to 0. It's a strong theoretical result. This formula we can apply independently in 3 different channels of accelerometer on the robot, which measure for you roll, pitch, and yaw angles. And you only fault on only one thing. What time happened this? It's also easy, because you can apply here 1 channel more and count the perfect coincidence between start of your interval of time and the end of this interval of time. Of course, will appear coincidence, partial or total, who knows? But if this process is repetitive, you can wait 2 or 3 periods of scanning and wait for the perfect one coincidence. Yes? And here you can see the graph. Maybe a little bit boring, but it shows to you that process of coincidence but by medians, it's convergent process. And look the time. 5 microseconds, 1 microseconds. But the first coincidence where the error beta is equal to 0 happens 3 times before 1 microsecond. You know, for the real robot, 1 microsecond, it's negligible time for to take information, for to take decisions, so on. And now about the last thing which I want to talk, and I've been mentioned this before, about the reason to take decision. Go on the right or on the left from the rock. Here you can see the right edge is closer to robot, and this is obvious. And sorry, cameras will give you the information that intensity of light here is higher than here. So it's low probable to find the intranspassable obstacle behind this edge and this one. But I have promised to you that I will give you one idea to take not traditional decision, where to go, on the left or on the right. Do you remember this landscape? It's Baja California. I'm from Baja California. There we have enormous solar activity. And this is not a good idea. Don't spend this kind of energy to extend the operating distance of the robot. We can, with the help of this solar panel, recharge the batteries and extend the operating time of robot, for example, for rescue operation in desert. If we have enough time, I will show you the real video of this region after the presentation to evaluate the importance of this task. Several dozens of people every year are going to this desert and disappearing there. They need a rescue, but it's extremely hot. The temperature is about 50, 60 degrees of Celsius, and secondary temperature from the sand, sometimes it's much more higher, maybe 100 degrees of Celsius. If somebody will fall down here, in a couple of hours, it's a dead body. The rescue personnel also are humans. So this task is typical task for a robotic rescue team. And if we have this solar panel here, it has 2 purposes. The first is obvious, recharge the batteries, but the second one is elegant also. It protects the batteries from the solar rays because the resource of batteries is falling down. Here you can see the tables. That batteries in different temperatures, working instead of 2 hours, just 40 minutes, for example. So we are covering with this solar panel the batteries. We are recharging the batteries with the sun energy. We are using the lateral mirrors for what? To increase the efficiency of the recharging mode of the robotic batteries. But from here comes an elegant idea for solution where we have to go on the left or on the right. Look at this, please. Here you can see the corners of solar panel. And if we will put in the corners 4 photosensors, the difference of signals in this bridge of wind will show us the direction of the solar zenith. Yes? We can detect with the same system where is the sun. And we will take the decision, go on the left, on the right, based on elegant arbitrary helper, sun. It will give us a calculation. Go in here, you have about 70% of efficiency in the recharging process. And going on the right, it's much more higher. This can help you to avoid the situation when the decision system will think, go to the left or on the right. It comes from outside, and this solution is arbitrary. It depends on the time. It happens at 12 o'clock or 6 o'clock or 7 p.m. Yes? So I don't want to stall your time more. And I suppose it is better to go to the question session. Thank you very much for attention. Anybody have a question?
Okay, I guess I will start with questions. Well, thanks for the presentation. I was wondering, what is the advantage of this range sensor where you are decoupling the emitter and the receiver versus the, let's say, industry standards or most common approach where both devices are in the same position and they are just spinning, and well, it seems to be like this kind of design, although it's very fragile, right? Because mechanically it's very well, it's problematic, but it seems to be kind of the standard there. So how can you compare with these existing methods, your solution that you were proposing here?
Thank you very much for your question. I can reply it only partially because this is a key point of this method. Emitter and receiver in this case are working independently. And when you are trying to calibrate this, it's a difficult, more engineering task than theoretical, but it have a kind of theory in this case. And this problem get the solution in the situation of this configuration. when the scanner works in the pair with cameras. To be honest, I can't explain you in detail this moment because this is exactly the topic of my PhD student, and he's preparing his publication right now. And all these secrets I cannot uncover in this case, but we get an interesting situation when you are calibrating just cameras, you need standards like chessboard, Aruko, Charuko, so on. When you are calibrating separately our laser scanner, you need exhaustive round of repetitive measurement of the objects with known geometry. But when you're working together, the calibration get an interesting result that you don't need any kind of calibrated standard. You can measure simply with any object which you relatively know that it's flat, and that's it. How we doing this? Sorry, this material still not published, I can tell you.
Okay, thank you. Any other question?
Like, thank you for presentation. Unfortunately, I missed part of it, but I read here some of your papers, quite high quality. I just wondering what kind of navigation approach are you using in your research of the mobile robotics? I mean, about path planner, SLAM. Can you give us some insight? What is now hot topic in your lab on this area? Thank you.
Well, to be honest, it's not SLAM exactly. We are deciding every time the simple geometrical configuration, taking into account self-orientation of our system. And each iteration, we are repeating this process.
But how do you build the map of the environment?
Excuse me?
Map, how do you build mapping? How do you make mapping?
Mapping?
Yeah.
Mapping what? The recovered
environment?
distance or surface?
Environment, everything.
Environment.
How do you localize? Do you use GPS signal or what?
No,
No.
no.
So you use LiDAR and cameras?
no. Our system is absolutely
So,
autosufficient.
and first you need to build a map.
The robot has done just one step. We know its recent position, and we are standing for the short time, short enough to give the possibility to scanner to obtain the necessary quantity of the dots. And then we have approximately described this surface with a limited quantity of discrete points. This is not very precise approach, but after that, on this figure, we are applying mathematics, simple mathematics of splines. We are describing with the equation of the known surfaces.
So you approximately understand where the obstacles are located and then building the path based on splines.
Yeah,
Okay.
Actually, it depends on the application. Because sometimes if you have a task, simply avoid collisions, you don't need do that. But obviously, such robotic tasks not exist. Normally, it is a team of robots which are going and all the surfaces scanned are stored in the memory, then transmitted to the common point cloud, and they are fused there to give the picture of whole scene.
Yeah. For outdoor, it's reasonable. For indoor, it's very critical.
Very close on your
Yeah.
microphone.
For outdoor, it's reasonable to have such approach, but for indoor robotics, you need very precise localization, extremely precise, by 1 centimeter quality. If you have time today, I will show you our Eurobot reset team, which is vice champions of the world in the mobile robotics. And we are building the fusion of sensors, including the lidars, odometry, cameras, global shutters, to reach the high quality precision. And we build kind of map and occupancy grid, and also all path planners adaptive to the dynamically changing environment. For outdoor, yes, there is no much challenges in terms of the precision and obstacles. So it makes sense to make it as simple as possible. Thank you so much.
Yeah, I totally agree with you. That is why we are lawyers of outdoor applications.
Yeah, absolutely. Anybody else would like to ask a question?
So thank you for the presentation. I have
You're
the
welcome.
following question. So as you show that you demonstrate your performance of your technology in harsh environments. So do you plan to use it not only on Earth, right?
Yes, why not?
Yeah, and how are you planning to deal with harsh environment conditions like dust, even in California, radiation that is extremely strong on Mars, and electronics possibly will not survive it. So, do you have plans to work on it, or?
Yeah, we still have plans because nobody can do all the work in 1 second. We
You have-
still not consider seriously this important and huge part of the task of robotic navigation.
At which year you expect your technology to be somewhere else? Like, do you have any specific date, planned timeline?
Sorry, I'm not prophet. I
Oh.
prefer to calculate, and here I have no enough material for to calculate this precisely.
Okay, thank you for the answer.
You're very welcome. Anybody have more questions? So if not, thank you very much for attention. Muchas gracias.